Good morning and welcome. I would like to open our online session of our MVP BIM conference. And for today's session, we have we had in plan 6 presentations. So far, we have only 4. So we will see, maybe some others will join us later on. But the first presentation is from Malgorzata Jarzabek-Rychard.
Yes, I'm here. Good morning.
Good morning. We are happy to see you here. And for all of you, we have your presentations pre-recorded. So we would like to welcome you before the presentation. Then we will play the recording, and afterwards there will be time for questions and discussion. So we can start with the first presentation. Please just confirm that you can see that all of you can see the presentation in the Zoom.
Yes. My name is Malgorzata Jarzabek-Rychard, and today I would like to present the research that I performed together with Professor Hans-Gerd Maas. The topic of this research is related to the automatic enrichment of indoor 3D models based on single images with unknown camera poses using a deep learning approach. 3D building modeling is a diverse field of research where data integration plays a very important role. In recent years, we could observe that the scope of BIM-related application is not anymore limited to purely professional usage. More frequently, it leaves space for various consumer products that rely on realistic 3D models which are created from special data. For a long time, the common concern in building modeling has been mostly focused to geometric reconstruction of the main structural building elements, so walls, ceilings, and floors. The second core part of building reconstruction, significantly less covered, was object recognition, where we label the parts of the data or already reconstructed primitives with semantic classes. Although windows and doors constitute a large proportion of every indoor object, many existing methods lack the capability to model them. This caused that currently we have available many 3D models which are limited to core elements. This factor, together with 2 others, so a very complex and frequently changing indoor environment, as well as growing number of consumer applications, trigger the need for the algorithms that will allow us to efficiently update existing building models and to increase its semantic coverage without the need for costly data acquisition and repetitive reconstruction. The goal of this work is then a semantic enrichment of existing indoor models by window objects, using information provided by RGB images taken at hand using amateur camera. Very important assumption underlying this methodology is its feasibility for consumer application. This means that the images are assumed to have unknown camera poses. The innovative idea of the presented solution is a parallel semantic recognition of the target objects in the image with its automatic positioning in 3D space. Our approach goes beyond pure texture matching and match deep learning detection techniques with camera pose estimation and 3D object reconstruction. The algorithm starts with a joint detection of window target object and the spatial layout of the corresponding room. The layout of the room extracted in the image is then matched with a 3D model. This allows us for the 3D reconstruction of the detected windows, which are solved by photogrammetric projection. And finally, the extracted window objects are subjected to the global regularization. The presented methodologic pipeline of image processing starts with the detection of chosen indoor object in RGB image. Besides target windows, we also aim at the detection of walls and ceilings, which are crucial for the extraction of the room layout, so of the edges of an indoor cube. To perform this detection task, we apply mask RCNN, so the robust deep learning detection framework. The results returned by this mask at that stage are partially overlapped and also can have an irregular boundaries. To improve these drawbacks, we apply morphological difference and subtract wall objects from the ceiling, which can allow us to obtain more regular ceiling shape. And in the last step, we extract the ceiling outline. Although deep learning detection techniques are a very powerful tool for object detection, they can show some deficits in the precise extraction of sharp edges. And in our research, sharp edges are crucial for the subsequent estimation of the camera pose. That's why, parallel to the last two operations of image processing chain, we apply one of the common detection methods, so the canny edge detector, to extract precisely pixels belonging to the edges detected in the image. In the next step, we merge these two results in order to improve the hypothetical position of the ceiling edges. So as an input, we use the buffer around the delineated ceiling that was extracted by mask RCNN, and as the second part of this input, we use the results of canny edge detector. Then we use the common part of these two images, and we extract only these pixels detected by canny filter that constitute the outline of the ceiling. The resulting edge pixels serves as an input for the vectorization of edges performed by half transform. So the straight line segments and their corresponding line equations are detected by finding peaks in half space. Window objects previously detected by mask RCNN and the vectorized wall ceiling edges extracted now are the final results of the image processing chain. 3D pose of a calibrated camera is determined by analyzing correspondences between 3D reference features and the 2D projections in the image. This means that we have 6 degrees of freedom, and if we would like to solve it using common 3D points, we will have to find at least 3 such points. However, in our case, we have only small parts of this 3D room visible in the image. This means that our set of common features is very limited, and we have to base our solution on the common lines. However, due to the clutters that usually occlude wall floor edges and shadows that hinder the detection of vertical walls, we have to limit this set of the corresponding lines to the free lines between the ceiling and the wall. Using the minimum possible size of the correspondences, we face the perspective free line problem. So, given the calibrated camera and the set of 3D lines in the 3D space and their corresponding 2D projections in the image space, we have to solve 2 tasks: estimation of the rotation matrix and, in the next step, estimation of the translation vector. The solution of the perspective free line problem is not uniquely determined. However, this potential solution differs from each other so clearly that it's enough to give just a rough initialization. So, for example, only the association of the image to the corresponding room. The final step of the presented methodologic pipeline is a 3D reconstruction of the windows detected in the image. The core idea here is a photogrammetric projections of the detected window pixels on the given 3D vector model. The projection is performed through the collinearity equations according to the exterior orientations parameters of the camera extracted in the previous steps. So once we have our image oriented in the 3D space, we could extract viewing rays that goes through each window pixel and then to intersect that viewing ray with a 3D plane provided by the input indoor model. The result of this operation is a set of 3D window points. These points can serve as a direct input to the best fitting rectangle algorithm that enable us to extract the 3D coordinates of the corners of the window. In the last step of the presented pipeline, window vector models are subjected to global regularization. The final layout of these windows is obtained by enforcing positional and shape changes, which are processed in the whole building at the same time. To verify the performance of the presented approach, we use part of the open dataset Stanford 2D 3D semantic. Out of this data, we have chosen 3 subsets that were used directly as an input for our algorithm. 3D point cloud of an indoor area, which serve as the base for 3D reconstruction of an input indoor model, RGB images belonging to this model, and RGB images that were acquired in other buildings, and these images are used for transfer learning by Mascar CNN. The 4th dataset is a reference camera information, which is only used for the verification of the estimated poses. To train Mascar CNN for the detection of chosen indoor object, we use a network with a backbone ResNet 50, which was pre-trained on the Open Deep Learning dataset ImageNet. For transfer learning, we used 100 images that were split 80 for training and 20 for validation. As a test dataset, we used 20 images captured in the target building, which directly serve for its further enrichment. First, we evaluate the camera pose estimation based on the comparison with the reference data computed for each image matched with the 3D model. The quality analysis is built on 2 indicators: angular camera orientation and 3D camera position. The absolute values of angular differences oscillate between 0.3 and 2.7 degree, giving the median value of around 1 degree. The median planar displacement of the camera position is equal to around 14 centimeters, with the value in the range of 5 to 35 centimeters. The estimated exterior orientation parameters enable to project the detected window pixels on the 3D walls of the input 3D model. To assess the performance of the automatic 3D mapping, the computed 3D window points are compared to the semantically classified reference 3D point cloud. The mean approximate distance between the both sets is equal to 3.6 centimeters. The visual comparison shows that all projected window points form proper layouted shapes, even preserving the shapes of occlusions. The main difference between the result and the reference set is in the sharpness of window boundaries. The final result of the presented approach is an input indoor model enriched in a vectorized window object. The visual assessment demonstrates that the presented approach can preserve a high accuracy fit between the objects detected in RGB images and the input 3D model. As a summary, I would like to highlight the most important findings of the presented research that was dedicated to the automatic upgrade of existing indoor 3D models using the information extracted from RGB images. The new insight of the research covers the parallel estimation of the image exterior orientation parameters with the recognition of target objects and their 3D reconstruction. To solve these problems, we propose a novel methodology that employs deep convolutional neural networks together with projective photogrammetry. Although the presented experiments are focused on windows, the algorithm behind can be easily adapted for other planar objects, which are usually visible in indoor scenes. The evaluation of the procedures shows that the method allows for the estimation of the camera poses with a median value of nearly 14 centimeters for the camera position and around 1 degree for its orientation. The quality assessment of 3D object matching reveals 3.6 centimeters of the mean approximate distance that indicate a high correlation between extracted object points and the reference data. With these results, we confirm that the proposed approach can achieve effective integration of vector 3D models with objects detected in single images, which are acquired in indoor scenes. Thank you for attention.
Thank you very much for this nice presentation. So now we have time for questions. our audience in here is quite small. You can see that we are only here, the chairs of the commission and our colleague who helps with the technical part. So I would like to give floor to our audience, which is online. If you have any questions to Dr. Jarzabek about her methodology she just presented.
No question.
No questions.
I have a question. The building, what I saw, I can see that there may be some ambiguity because every room can look more or less the same. You know, also in administrative buildings, you have one type of room and it's like copied on the floor. So when you estimated the camera pose, did you have some problem with this? That there was a mistake that the algorithm found the pose in a different room?
So as it was shown here, we need some rough initialization.
Yeah.
That I mentioned about. And this means that when we are capturing, so we can just use the normal camera and can capture images at hand. And then we have to label the images to the room.
Yeah, okay.
Because of course, this what you said, it would be very, very difficult because especially for such buildings, like for example, university or some company buildings, many of the rooms are exactly the same, and there is also not enough structure on the wall to differentiate. That's why we have this rough initialization. So the association images and room.
Okay, thank you. I missed this probably.
Thank you.
Well, I would like to ask, maybe I missed it in the presentation. You were mentioning the camera that you use, just let's say standard cameras which we can get anywhere, and because the number of geometric features you have for the orientation, I understood it's only these 3 lines which you extracted for the ceiling. And what do you do with the parameters of inner orientation? You just take the focal length, which is connected to the camera from the producer, and you neglect the lens distortions and the other parameters.
Yes, exactly. So the we already started this experiment, having assumed that we have inner orientation. So this is also a very interesting topic, and we would like also to make some further experiments about that, to also check these inner parameters. But up to now, these experiments that you have seen, it was with the assumption that the interior orientation parameters are known.
Okay, thank you. And my last question, you used this RCNN for masking the windows and finding the windows. Is it the best option from all these possibilities we have with convolutional networks, or did you how come that you chose this special let's say implementation? Were you evaluating also some other possibilities?
So first, I wanted to focus on some detection network. So as I said, the detection that will only detect the objects. So that will not segment the whole 3D scene or all the image, but just detect the object of interest. But also the idea for the future work is to check another neural network, for example, some networks for the segmentation of the whole image, and to compare them. So this is the idea for the follow-up paper about it.
Thank you very much.
Thank you.
I will ask again if anybody from the audience has any question. If it's not so, thank you very much for your interest.
Thank you very much for your attention.
And we can continue with the next presentation. So I just would like to check that Juan, Enrique, Nieto-Julián is with us. Just welcome.
Hello.
Hello. And
we only participate 8 listeners. I had problem with audio and video.
Okay, that's fine.
And the students are waiting for coming in class. Student are waiting.
Fine. So
Thank you very much.
We will listen to your presentation now, and then there will be time for discussion.
Welcome to this paper entitled IFC Data Mapping Based on the Parametric BIM Coding for an Efficient Workflow in the Quantification and Management of Construction Costs. It is a collaborative work between the professional from the construction sector and research from the University of Sevilla. The BIM, Building Information Modeling methodology, moves in a collaborative data managing environment to monitor and control the design, planning, cost control, construction processes, and building maintenance, but to enjoy the benefits of BIM in its fifth dimension, 5D, cost and time saving, it is essential to properly plan each phase of the project and manage the information effectively within the same team. This research aimed to validate an effective method from the creation of the information of a constructed entity using code disaggregated by budget line item necessary for the mapping of data in the structure of the IFC 5 industrial foundation classes and the confrontation with the filter rules in quantification software. Specifically, define the entity of construction element of the model by creating a coding of and parametric description of the budget item. All elements will be mapped following an IFC structure and using the ECOP standard. They are involved with a consistent and technically rigorous data structure, which facilitates interoperability between BIM software. Finally, this information will be collected in the 5D BIM software to compare it with the information established in the rule corresponding to each item. A considerable number of applications for the evaluation of construction costs coexist in the market. 5D BIM, it is working in an open BIM environment, reinforcing the collaborative workflow based on AFC5 connection. The work progress is a consistent, generally based in the mapping and information and the subsequent elaboration of rules to filter the parametric data associated with the 3D element of the IFC file. This rule will be defining the cost evaluation and quantification software. But one of the problems involved in the elaboration of the information filtering rule is that necessary to generate a large number of rules for a specific element defined by different budget items, combining the different variables. Has a work methodology produced is established based on a first organization of the information which involves structuring the geometric data and the classification of element BIM. The operators analyze the data to avoid unpredictably indeterminate and the quantification. For it, a building with 4 floors, adult, grow, and one of the basement level is chosen to generate an accurate measure of the structural model we producing to modeling in ArchiCAD. The SIP quantities of software is used to generate the budget by linking AFC5. To create a twin information to the budget database, specific parameters are created as pre-established variable, material type of concrete and amount of steel. Other parameters, section and height are given by the same BIM platform. The database is created using the SIP software in which different budget items for columns and reinforced concrete walls will be organized. Various classification systems has been used for the elements of BIM model classification ArchiCAD being class and SIPE, the latter being essential for interoperability with quantity software. The image below shows the classification of the column P37. In the ArchiCAD Property Manager, the data are parameterized for the creation code and description. The reinforced concrete column code property is generated by concatenated data. Fixed code plus coding according to concrete plus coding according to amount. The reinforced concrete column description property is also generated by concatenate and fixed text followed by the code, based on the specific parameter select. In the list in the Property Manager section, specific row categories has been created to contain the properties of quantities, measurement. In the case of the column concrete code, description to concrete column measure line, code from work description. The result of parametrization is the creation on amount code and description depending of the select variable. In this way, a hyperlink scheme is made in ArchiCAD to list the element classification. The next step is to structure the information for this IFC export in ArchiCAD Translator. IFC property mapping for export section and organization structure file for item is established similar to the ECOP system. From the IFC building element section will be created at a set and the parameter. The part code parameter will be referred to the 18 budget line code. The part function parameter refers to the description of this game. Before exporting the BIM model, a specific IFC translator is made in ArchiCAD, activating the geometry preference and associated data that you want to select. An IFC translator defines the rules for deciding which element should be converted and how they should be interpreted. Here you control and settings such as the IFC schema, type and conversion, present model feature, type mapping, geometry conversion, property mapping, data conversion, answer conversion. The model is exporting in a IFC file, and from the IFC viewer on the market, it is possible to review the elements of the model and structure data in the measure per set. Let's see the exploration. The IFC model is now applied to the BIM Collab viewer, where a filter criterion has been established to analyze the type of for work, depending on the code or description of the parameter coding of function. Open BIM quantities is integrated into Open BIM workflow via BIM Server Center platform. The software exchanges information with the linked BIM project. Import 3D IFC model. Open BIM's quantity show the 3D view of all elements that are imported. Quantity has a data collection system that is filtered through rules to identify an element depending on certain characteristics. IFC classification elements name material geometry and relate them to one or more item budget from a price-based file, standard format or property. In the measure criteria section of SIPE quantities, as a direction relationship has been established for the parametric that meets a code in the budget database. It is true will be cross that information with the corresponding budget line, and the export will be automatic. The workflow using rules for a direct relationship between the elements parameter and the budget item generated a large number of rules depending on the combination of variables. For example, we have the column elements defining, but this is material A, section and amount of steel. In this case of non-restriction, the information will have the following combination by type. For the above case, the combination to create a rule based with the budget item are 120. By applying the proposed system, reduce the number of combinations, researching 22. The data sets combine the type of concrete with amount of steel. But if we separated these two variables, the combination of rules will be reduced to number of system rules. The method analyzes, tests, and tested based on a adequate structuring and classification of data of the elements that make up the BIM model has been productive and efficient, avoiding random decision-making by the operator who analyzes the quantification that may lead to error or inaccuracy with applying the metric. The result of this study showed that combination of parameters can be considerably reduced. The percentage of rules will decrease to a ratio of system 120 in an AFC information mapping process to be validated in software of quantification and evaluation, improving data exchange and interoperability in an international environment. We want to express my gratitude to the organizing committee for choosing this work. Thank you.
Thank you for the presentation. And now there is floor for questions from the audience. So please raise your hand and unmute and ask questions, or you can write the question to the chat. So are there any questions? Maybe I could ask, is this just a concept, or did you discuss it already with some people from business or from practice? Could you hear me? Okay, so maybe we will close this part. If you can read the paper, the whole paper in the archives, and possibly if any of you has questions later on, you have their contacts to the authors, so you can communicate your questions individually later on. And we can move to the next presentation, which will be given by Sebastian Schilling from Dresden University of Applied Sciences.
Yes, good morning from Dresden.
Good morning and welcome. And we will listen to your presentation first.
Yes, all right. Welcome to my presentation. My name is Sebastian Schilling and I am research assistant at the Faculty of Geospatial Information on the HTW Dresden in Germany. Together with my co-author Christian Clemen, I made a research to practical examples on BIM-GIS integration based on semantic web triple stores. The integration of geodata and building models is one of the current challenges in domains of architecture, engineering, construction, owner and operation. It is not possible to map data from building information models to geographical information systems, because these are different domains. So direct mapping of data from BIM to GIS or GIS to BIM or into both ways is not possible. So these two domains have fundamentally different perspectives on things, for example, buildings. In GIS, buildings are described in the context of city models, and in BIM, buildings are described in the context of construction or operation. One approach to solve these problems is to use the semantic web technologies to link same things between domains. This approach is already improved, and in the next slides I will show you in short how semantic linking can already be used for BIM and GIS integration. So in semantic web we use ontologies as schema for describing data in a domain. There's not only one ontology for each domain, so there can be many ontologies, but for simplifying I will use only one ontology per domain for demonstration. In the first step, we have to reach out if there is already an ontology which describes our data. If not, we have to create a new ontology. So when we have the BIM and GIS ontology, we have to match them together. We can do this matching by finding classes defining the same individuals, for example, with building classes, and we can also add new links between BIM and GIS classes. Then we can use these ontologies to convert data from both domains into the resource description framework and domain-independent format of the semantic web. And also we can create links between instances of this RDF data. Then we can store all these ontologies and RDF data into a triple store. And now we have the chance to answer questions over this integrated data by querying the graph. So for example, here we can use the Sparker protocol and RDF query language for making requests. So this is the pure semantic web approach, and this approach works for many data integrations. All informations are stored in one triple store, and queries can made from the BIM and GIS domain over all data to answer questions. But here we saw some problems. In triple stores, geospatial data can't be stored and queried as efficient as in object relational databases. And in triple stores, none or only a few spatial functions in 2D are available. Also, geometry is stored as well-known text, and each geometry has its own CRS URI and can be transformed. So here are some problems which we want to solve with an hybrid approach. In our implementation, we want to combine a triple store and a geodatabase and link them together. So then we can use the advantages of both technologies. In the triple store, we want to store the non-geometrical data, and in the geodatabase, the geometries. For implementing this hybrid approach, we use some technologies. For example, we used a microservice architecture for the data processing and import. A microservice architecture allows us to create little and lightweight and independent pieces of software which we can link together to achieve a common goal. And this architecture style has the advantage that services can be easily added, updated, tested, and deleted. And these are also advantages of Docker. So we use Docker containers for each microservice. The services are implemented in Java, and here we mainly use the Spring framework. As triple store, we use GraphDB from OntoText, and as geodatabase, we use PostgreSQL with the PostGIS extension. Here you can see our microservice architecture. This is an architecture under construction. Until now, it consists of mainly 7 pieces. The first component is the discovery server. The discovery server manages the communication between the services. And we have also a configuration server who manages the configurations for each service. These 2 components are in the mostly microservices. Then we have the converter service or converter services. These are services which convert different file types into the RDF framework. Then we have the file input handler. He orchestrates the processing of all incoming files and imports the RDF data into the triple store. The geometry handler extracts geometry from the files and imports it into the geodatabase. The triple store is used to store the non-geometrical data, and the geodatabase to store geometries. Now I will show you the data import in a little more detail. So the user sends some files to the file input handler, for example XML, RDF, XML, Turtle, TXT or IFC files. The file input handler decides how to process these files. If these files are TXT or IFC files, they are sent to the converter service, and he converts the data into a RDF turtle syntax and sends them back to the file input handler. If the files contain geometries like XML files, they are sent to the geometry handler, and the geometry handler extracts this geometry and sends them to a geodatabase. The geometry handler gives back some metadata and an IRI, which I will explain next. All this data, the RDF files and created RDF triples, the metadata and the IRI are sent to the triple store. And now the IRI is also in the triple store and can be used as external link to the geodatabase. And I will explain you how we create this IRI link. So for understanding, we use the GeoSparkle ontology for describing geometries in RDF in our triple store, and we extend this ontology. We add a class geolink and a predicate URL, which extends the geometry class of the GeoSparkle ontology, and we add also some more topological predicates. So the geometry handler has an API for serving the geometries from geodatabase. This API is conformed to the standard OGC API feature part 1 core. And this schema you can see here is from this standard, and we use them to create our links. So here you can see an example link. This link contains of the collection ID. This is the table of the geometry in the geodatabase, and the feature ID. This is the primary key of the geometry. And with this schema, we can create for every geometry one individual link and store them into the triple store as the external link. So now we have imported all data and created our links, and now we can request this data. So if the user has a question, he can send this question to the event handler. The event handler will make a Sparkle query from this question and execute them on the triple store. The triple store sends a result, and the event handler checks if this result contains a geometry IRI. If this is the case, he executes this IRI on the geometry handler API, which sends an SQL query to the geodatabase and gets back the geometry, which is forwarded to the event handler. The event handler merges all results together and gives back the answer to the user. And now, in ideal case, the user didn't see something of this internal linking. So the user gets the geometry and didn't have to execute this link. Now I will show you our approach on a little test scenario. So we have a use case, we want to build a house, and we have the source data, a digital terrain model, geographical and non-geographical data about the land usage, and a georeferenced BIM model. On the right side you can see all this geometrical data. After we import all data, we can query questions. So here we have question, which forms of land use are affected by constructing the building, give the geometries of these land use. Here you can see the Sparkle query. This query gets as a response a table which contains of two land use types, forest and grassland, and these land use types have a geometry IRI which can be executed over the API, and then we get the geometry representation. And these two geometries are the two polygons of the image before. So here we can see that our result is right. So now I will come to a conclusion. We can say the approach for using pure semantic web technologies for BIM and GIS integration is not suitable if the data contains geometry. Until now, triple stores can't process geometry data as efficient and extensive as relational database. So our hybrid approach with triple store and geodatabase can challenge these problems, but we need some services for input and output the data for better usage. And the microservice architecture we use can easily extend by new applications. And with this, we will come to the outlook. So now we imported IFC data into the triple store, but the geometry is not serialized in the RDF representation of IFC very well. So in the future, we will also store the IFC geometry in another domain-specific database, for example, the BIM server, and create links like I presented here. And also we want to extend the ontology to create more BIM-GIS relations. So with this, I will come to the end and thank you for your attention.
Well, thank you for your presentation.
You're welcome.
Please, are there any questions from the audience? So far, there's a question here. Please.
I have a question. Did you also use GIS data which are more related to facility management? Because I can imagine that in those data, the building is like stored like more complicated, like more in detail, I mean, and the relations between like facility management GIS data and BIM can be different. So did you try also your approach to those kind of data?
No, until now we only have this little test implementation. So we are at the beginning of implementation, and so we have not tried to extend our relations to more complex test examples.
Okay. Thank you. Thank you for the presentation.
You're welcome.
Thank you, and we look forward to the next work you are going to present in near future. And with that, I think we can move on. And on the list, the next presentation should be from Alexander Wojnarowski, but I don't think that he is online with us. Then there should be a presentation from Bakhberde Adebiyet, but no one from Kazakhstan is with us here who could present, and we don't have the presentation recorded. So then we move to the last presentation of this.
Actually, there is Elmira Orynbassarova presented, and she's the co-author of the
That's right.
of the paper. So
please, Elmira, could you clarify if you would like to present, because we don't have your recording.
Hello.
Hello.
Hello. I'm Elmira. Nice to meet you. I will be presented by Adebiyet Bakhberde, MSc degree student of the second year, SATBAYEV University. Thank you. Please, Bakhberde.
So you can share the screen.
Could you please give the access to make the demonstration of the screen, please?
From
Yeah. Okay.
Okay. Now it's okay. Thank you.
Okay. Good afternoon for everyone. I am Adebiyet Bakhberde, second year master's degree student at SATBAYEV University in Almaty, Kazakhstan. As you can see on the screen, our topic today is create 3D model using UAV and laser scanning data. The main goal of is to create interactive detailed 3D model of SATBAYEV University with VR and AR effects. Also, this job is part of my master's dissertation. Next. My talk will be in 3 parts. In the first part about create 3D model based on UAV data. Then in the second part, building 3D model based on laser scanning data. Finally, I will go on to talk about integrate data with AR, VR technologies. SATBAYEV University. So I want to say a few words about our beautiful university. It's located in southern capital of Kazakhstan, characterized by mountainous landscape and lots of greenery. SATBAYEV University has historical value in Kazakhstan as it is the first technical university built in 1934 since the Soviet Union. Also named after the great Kazakh geologist Kaныsh Imantayevich SATBAYEV. Next. Now let's move to first part of my talk, investigation of an 3D model with help of UAV data. For aerial photography was used drone DJI series Phantom 4 Pro version 2. Так. First shooting techniques which we show in right side. The altitude was 80 meters. The camera tilt angle is set 75 degree, and for more overlap and for 3D maps. Total shooting time was approximately 25 minutes. Next, okay. Then global positioning use ground control points, GCP, the accuracy of determining them in plan 1 centimeter, in height 2 centimeter. Device from Leica series GS16s, in total 22 points were captured in 30K mode. So talk about results. Here you can see the basic settings, also results as an orthophoto map, digital surface map, and dense point cloud with 3D model. It's a loading image, quality of orthophoto map. Also digital surface model, DSM. And I want to show quality of our work. Okay. Here we have some defects, depends on blind zones and trees, other buildings. Okay, move to next part, laser scanning. Nowadays, one of the best modeling solutions, but at the same time, from a large amount of data, we are dealing with complex processing. Pre-processing we make in Leica Cyclone register. Scan data from multiple setups captured with the RTC 360 laser scanner and automatically tracked and processed by the unique visual inertial system, VIS. Okay. It's a Cyclone Field 360 app, and there are our stations marked red circles, and each stations have connections with different kinds of colors, which show incompatibility of groups. Accordingly, a red line means incompatibility less than 20%, yellow between 20 and 40, and green more than 40%. During the process, we met some kinds of issues, like shown in this picture. This kind of issue we can also check and solve manually, move vertically or horizontally. Then, after finishing, software automatically recalculated. This is a report of our work, which consists of the results of the total error, which is 4 millimeters, overlaps, 41% compatibility, 51%, and compatibility between point cloud graphs. Next, so after finishing all this data, export to SketchUp. Using plugin Undead help to optimize our point cloud, classified, for example, by Z attribute or RGB color or density. And also we may divide into small pieces for comfortable digitizing. For example, our first building named NK, then classified point clouds, digitizing windows, door, and other piece of our building. Next, visualization. In software SketchUp, we also add point cloud and our finishing model. Next, integration of receiver data with VR and AR technologies. There are three reasons why we realize it. First, advertising purpose for new students building navigation, especially during the year of online education. Due to the pandemic, it's more important to show our university buildings for new students. Second is for reconstruction work. As I note, SATBAYEV University has historical value, and the model allows to make measurements and calculations in SketchUp software. For building monitoring purpose, further geodetic works or point clouds will be loaded into the model. In here, you can see our university, this office registration, and the second building is NK, and also our third building named GMK. Okay, 1 minute. I also want to show our integration with 3D tour, 3D indoor tour with interactive buttons. Okay. Okay, we have panorama sense make with first it make in Twinmotion software. Then we also connect with our panorama photos in make by mobile phone, and also we move from points and also indoor model our university. Thank you for your attention.
Thank you for presentation. Although we expected to have it here pre-recorded, so it as the other did, but nevertheless, we saw it now. Are there any questions from the audience? Definitely, you created a very nice model of your university. You combine the different technology. Nevertheless, I can see that you can see some novelty in your approach, because what we can see here in all these presentations we had so far, the goal of the conference is to show some new steps, new ideas which are in this domain. So where do you see the novelty of your approach which you applied, or did you apply the standard procedures, standard methods?
Okay, it will be integration with AR and VR effects. Also, we improve our work, and how I can say it's a part of my master's thesis, and we improve our work. Also add also AR effects in future, also VR effects.
Thank you. So, any other questions?
I have a question. Hi. I have a question about the AR application that you want to do something for mobile with a really augmented reality, that you mix the digital model with a real view of the lens of the phone, or how you plan it to do the AR implementation?
Okay, yes, thank you for question. Yes, we want to open access for everyone who want to see our university, and also in VR AR models we use for everyone. For example, apps in mobile phones.
Yes, and it will work like you will see the university, and the augmented reality will have inside the maybe some text or photos or something like that. Or
yes,
how it will look like.
Yes, I was thinking about it.
Okay. Okay, thank you.
Thank you.
Okay, thank you. So by this, we finish this presentation. Thank you very much for joining us. And then finally, we go to the last presentation, and we have Francesca Biolo with us from the Polytechnic University of Milan.
Yes, good morning.
Good morning. Nice to see you. And we will listen to your presentation first.
Okay.
No i nemáme její prezentaci, ale
Aha.
jsme skončili všechny nahrané.
Sorry. I was somehow confused. I thought we have your presentation. Francesca, please.
Yes, what? I'm sorry?
Sorry. We don't have your pre-recorded presentation.
I sent you some days ago.
Yes,
I'm sure. I sent you the link to download it. Or, the presentation and the recording of my speech on the presentation. So if you want, I can resend you these, but...
Just a second.
Pardon,
We apologize. We had a small confusion in here.
Don't worry.
We have it by like recorded as Francesco Ciusetti, and so we were your co-author. So we
don't worry.
Confused here. Sorry for that, and we will start the presentation now.
Good morning, I'm Francesca Biolo, a PhD student at Politecnico di Milano. Today I will describe you a research carried out with my teamwork about the idea of heritage BIM and the approach to this method. So let's start. As we'll know, today's world is facing an increasingly technological presence that led processes, objects and services to change shape, taking on a digital character. We are living the digital era. In this context, the construction and architecture sector has also seen several changes concerning different areas of work: survey, 3D modeling, facility management, information fruition, and so on. A particularly significant revolution was that concerning the BIM approach, so the building information modeling. BIM workflow is now part of a common scenario in this sector. The introduction of this tool represents an international reform. As we know, this work process has developed for new buildings and now represent a powerful tool for managing all the phases of this building. BIM represents specific software, and there are now clear and well-defined standards regarding work processes. The use of BIM is now widespread and is often mandatory for all new construction intervention. Although in the various countries, the deadline for the mandatory use of BIM for existing buildings, so HBIM, is increasingly stringent. For example, in Italy, it is 2025. To date, however, it is difficult to think of a standardized approach for HBIM. The working models born for new buildings have also been adapted to pre-existing buildings, so structure with totally different feature. Moreover, these buildings bring with them specific information that can hardly be standardized, like that about history, for example. For us, it's not possible to think of adapting the building approach to an architectural heritage. The experience gained with the BIM world, however, must be used together with the opportunities offered by this digital era. To develop a new approach to the digitization of cultural heritage. It should understand the necessity of this kind of structures, but also enhance and preserve the architectural and the information heritage of our territories. So we started thinking about a new method to develop an heritage BIM model. This work is not yet finished, but it starts from a precise idea, that is to define a standard tool that can also allow the systematization of information that did not find a place in the current BIM. This information is often linked to the history of the building, to the events that characterize them and their specific peculiarities. Not being able to insert such data inside a digital twin means losing part of the assets. Being able to organize this data, linking it to a digital model, stimulates the knowledge of the building by promoting the enhancement and conservation. To develop this idea, we based the work on a particularly complex case, the Castello Sforzesco in Milan. The castle is a complex architecture of considerable size. Its history starts into the 13th century at the time of the Visconti family. The events and transformations that have affected it are many, so generating a huge amount of information, data and material. A building like the Milanese castle represents a perfect test for the correct functioning of the work model. So the work carried out is an answer to a growing need in the architectural field to transfer the management, conservation and dissemination of cultural heritage to a digital environment. It is a matter of providing a flexible solution that respects the feature of the individual case without changing the main framework and standards. The diagram, so the image you see in the slide, represents the summary of the working model that has been structured with reference to the case study. It is composed of a central core and several information levels that complete it and coexist in parallel. So let's analyze it. The general digital object with its geometric information remains at the center. It is a 3D digital model of the building inserted in a BIM-GIS system and completed with a series of information layers, independent in the level of detail. As we said, the central 3D model is completed with these levels. The latter deals with all the information assets. They are all data you would expect to find in a BIM model. But in addition, always in the digital copy, it is necessary to transmit this information by loading them with the historical factor. Finally, we also find all the information strictly committed to architectural heritage, such as documentation, history, previous intervention, and so on. Layers are treated following the needs of the different information, homogeneous within a single package. Indeed, the various types of data may require different methods and processing technique. All this leads to the development of multiple approaches to digitization, but collected within a system that coordinates them, evolving the idea of a single and unique model. Now, let's see some cases that we have been developed, so some insights. The first one deals with documentation, storage, and management. Architectural heritage is often associated with a wide number of bibliographic, iconographic, and cartographic resources. These data constitute precious knowledge and fundamental information for understanding architecture. This documentation is part of the information asset related to the cultural heritage. So information is often in several archives. This is the problem. So we find these resources in archives, libraries, and offices. It is sometimes difficult to access. The idea of document archiving must be somehow changed, thus finding a more effective way to tell the tale of architectural heritage. The solution here exposed consists of an information level dedicated to archival material based on the use of tags. The system uses 4 levels of tags that create multiple typological and thematic categories. Thanks to these tags, each digital record is equipped with multiple attributes. Latter act both as an organizing principle for the document during the storage phase and as a research tool. On 3 of these tags, those of category, typology, and content, we base the organization of the material and its use. Document can be researched through a vertical navigation by material type or through a horizontal navigation suggested on the basis of the content tags. Finally, by using a geotag for each document, it is possible to visualize the information of on the central model. Based on the content of the document, a pin will be created that refers to the architecture in general or to a part of it. A further part of the work deals with solutions for making digitally available not accessible or not visitable places, and to offer a digital alternative to the traditional visit. This part of the work was dedicated to setting the way of use for digital objects through the ICT solution, such as augmented reality and virtual reality. This solution is spreading a lot as they exploit the new digital habit of people and technology now so common, such as smartphone and mobile devices. This study was made on our case study, so on closed spaces of the Castello Sforzesco, exploiting modern survey technologies like laser scanning and photogrammetry. The idea is to report on the digital twin the indication of the spaces of which there is a digitization product. In a BIM-GIS environment, a point or a surface element will suffice for this operation. So this object can be completed with attributes that describe the available material, including a link that refers to an external web page or an app, an application on which the material is imported, where the real virtual experience takes place. We find a particular page that offers this opportunity, that is 3JS. This solution allows obtaining both an informating system completed with the connection to the virtual insights and portal accessible outside the environment for more touristic use. The last in-depth analysis concerned the organization of information relating to external systems that interacts and affect the architectural asset, such as greenery, infrastructure, paths, and much more. These type of information levels become a super tools for decision. For this section, the typical feature of the GIS world and its software have proven to be an optimal solution. For the case study, a simple trial was carried out analyzing the relationship between the Castello Sforzesco and the surrounding greenery of Parco Sempione. This goal is to verify how these two systems interact with each other and whether the root system can be treated to the already fragile structure of the underground Pirlanda. Summarizing the operation, the data relating to the trees were introduced in the GIS environment, especially the depth of the roots in relation to the tree species. For each tree, a buffer was set on the basis of the root depth, thus observing the critical point of the interaction between the greenery and the underground structure of the castle. This information provides support for the maintenance operation of the structure, indicating the most fragile point, for example. These insights are only three, but the information levels that can complete the digital twin of a cultural heritage are many. Other important information is that relating to the historical and architectural evolution of the building, the mapping of degradation phenomena or the structural instability, information about the facility, and much more. The work done so far is only part of a larger project that will continue in the future. And as we said, the idea behind all this is the belief that it's necessary to review the idea and the structures currently used for the heritage BIM, opening up to other more flexible solution and perhaps more respectful of the tangible and informative heritage that we are dealing with. So that's it. Thank you for the attention.
Thank you very much for the presentation. It's, I would say, inspiring concept for many historical buildings and cultural heritage places. Are there any questions?
Can I give you a question?
Of course, please.
So, hi, Francesca. I'm really interested in your presentation and above all on the information layers concept.
Okay.
Because I think that we have to work in this way with BIM models to integrate all the information we need about the building. And I was thinking, do you think so that with this approach it is possible to have different BIM uses with the same BIM model? So, for example, to use this the same BIM model for documentation, but also for some simulations such as energy modeling, structural modeling, or facility management data?
Yes, so this is the first step of this project. It's my PhD research, so it's a in progress work. But the idea it's this. So we are trying to define a way to keep together all this information, to make all the analysis, study, or to have all the information useful for the management, for the comprehension of the cultural heritage, and to understand them, but not in a usual traditional way. So we try to make an HBIM model with some standards made from a BIM group here in Politecnico. These guidelines are made for new buildings, and we try to use them for a cultural heritage. So the castle of a city near Milan, but we find a lot of difficulties. So we want to transfer this method, this instrument, this important instrument, in a new place with new rules and approach. So the idea is this, so to make this with the time, so develop better the method, but yes, this is the aim, but trying to make different approach. So a place to collect all, but where we find different method, different layers that live in an autonomous way. Okay, so collect but not interacting in a way. So if we can say this, but linked to the same 3D model.
Okay, many thanks you, and thanks you for your presentation. It was very interesting.
Thank you.
I have another question.
Yes.
For your presentation, Francesca. Like you pointed out very well that the BIM is a lot about collecting the data about the building, but a very important part is also sharing the data with the other, other interested people in the life cycle of the building. So did you already think about some common data environment where you can transfer the data, or do you put all the data, all the possible data to IFC model and make the IFC model transferable to other interested groups? Well,
So,
did you think about it?
I hope to understand the question, but the idea is to make the idea is to have this model, this place of knowledge, okay, for some specific people that deals with the management of the building, that deals with the some design project and so on. Some of this information for us, it's important to transfer to normal people. Okay, don't like the information about the bibliographic, cartographic information, so the AR and VR reality. So some of this information we must consider to transfer to other people in another with another path. So arriving externally, okay, to something, to a web page, to a portal, to a system that is also linked to the central model with the attributes of the GIS, software. I hope to understand your question and to answer it.
Yeah, thank you.
Okay.
Okay, so I have a question, if I can. Okay, so I have a very short question related to this before. So when you already have your integrated data, in which software you can visualize the results?
Okay. The idea is to use GIS, so ArcGIS, okay, to visualize the central model with all the layers, all the attributes, all the information. If you need to integrate in some way some information like the augmented reality, we want to try to link all this to some external system. So to prepare some place where we can to which we can arrive from the link, okay, connected to our central model. But the idea is to organize all in a GIS software. And this is all. This is for our preparation, because we deal with a lot with GIS and with the territorial information. So we work a lot with it, and this is and we transfer all our models, our approach to this for, I don't know, for habits maybe, but we find a lot of useful instrument in this type of software.
Okay, so are there any more questions from the audience? Doesn't look like. So I would like to thank to all presenters for their interesting presentations and discussions. And we can close this session now. And according to the program, the next session on BIM for construction and cultural heritage starts at 11:30. So you are welcome again to join online if you are interested, and continue with listening to presentations and discussions. So thank you very much to all presenters again, and see you later on.
Thank you.